In September 2005, Norway's hydrographic service, Sjøkartverket, was out in Hafrsfjord, a sheltered inlet near Stavanger, testing new sonar equipment as part of its hydrographic work. Their objective was seabed mapping, not aviation archaeology. The survey vessel deployed a side-scan sonar system to image the bottom topography. As the sensor swept a sector near the island of Prestoya, the acoustic return displayed a distinct geometric anomaly disrupting the natural silt patterns. The dimensions were too consistent for a rock formation and too complex for a shipwreck. The operators marked the coordinates and froze the anomaly in the ship's log. The return signature measured roughly 57 feet in length, with a wingspan stretching to about 72 feet. The outline suggested a large twin-engine aircraft resting inverted on the bottom. Analysis of the acoustic shadow indicated that the wings were not flat against the sediment, but suspended slightly, implying the structure was resting on its dorsal section. The profile of a wartime loss. The specific geometry of the planform pointed to a Luftwaffe maritime patrol aircraft, missing for 70 years. The target was identified as a Heinkel He, 115 BC, a large German float plane designed for torpedo attacks and coastal reconnaissance. Historical records correlated the position with Werknummer 2398, an aircraft attached to the 1st Squadron of Coastal Aviation Group 906. The dossier confirmed it had been lost in a landing accident during the Second World War. For 7 decades, the airframe had remained undisturbed in the cold, dark water, its location lost to time until the sonar pulse illuminated its resting place. Side-scan sonar works by throwing high-frequency sound in a wide fan toward the seafloor. Hard surfaces, aluminum, steel, answer back with a strong return. Behind them, the system records something just as important: silence. That absence becomes an acoustic shadow. By reading its length and angle, surveyors estimate how far an object stands proud of the mud. In Hafrsfjord, the shadow was crisp and geometric, not the messy smear of a debris field, but a coherent airframe holding its shape. The depth of the wreck was established at 151 feet. This depth placed the aircraft well below the reach of recreational divers and surface wave action. The water at this level in the fjord is characterized by stability and darkness. More critically, the seabed is composed of soft silt with very low oxygen. In this kind of low oxygen, low energy burial, many of the biological and chemical processes that normally chew through wreckage slow dramatically. They do not vanish, but they lose their speed. In a high-energy ocean environment, 70 years of saltwater exposure would reduce an aluminum airframe to a skeletal, corroded lattice. In the static, suffocating mud of Hafrsfjord, the decay clock runs slower. The sonar return suggested the Heinkel was not a scattered debris field, but a coherent airframe with its major geometry still in place. Fine detail, like paint condition or glazing, would have to be confirmed by divers, but the outline alone hinted at something unusually complete. This preservation presented a rare opportunity for the Sula Aviation Museum and its team of volunteers. Recovering a complete example of this rare type was theoretically possible. However, the clarity of the sonar image concealed a significant threat. The aircraft had not crashed in the traditional sense of a high-speed impact. It had settled. The same soft silt that cradled the aluminum for generations had also created a powerful seal around the wings. The aircraft was not merely resting on the bottom, it was embedded in it. Any attempt to lift the airframe would have to overcome the friction and suction of the mud without tearing the vintage structure apart. The discovery in 2005 closed the gap on the aircraft's location. We knew what it was, we knew where it laid, and we knew it was remarkably intact. But the transition from a digital image on a survey screen to a physical object on the deck of a barge would require 7 years of planning. The environment that saved the plane was now the primary obstacle to its recovery. Before the engineers could design a lifting plan to break the grip of the mud, they had to understand exactly how the aircraft ended up at the bottom of the fjord, and what specific forces had acted upon it in the final seconds of its flight. The preservation of Werknummer 2398 is not an accident of history, it's chemistry, the kind written in dense, fine silt and stagnant water. Down here, oxygen is scarce, and that scarcity slows the reactions that normally strip paint, eat fabric, and turn thin aluminum into flakes. But that same burial also traps seawater salts deep inside seams and lap joints, setting a timer that will start the moment the aircraft is disturbed. Corrosion in seawater is driven by salts, moisture, electrical differences within the metal, and often oxygen. By sinking into dense, low-oxygen silt, the Heinkel did not become immortal, but many destructive reactions and biological attacks slowed to a crawl. The trade-off was hidden. Chlorides lodged deep in seams and riveted layers, waiting. Once exposed to fresh oxygen and drying air, those trapped salts can turn a stable wreck into a fast-moving failure. The chain of events that put the aircraft into this silt began on December 28, 1942. The loss accounts point to a simple, costly decision during the landing phase. The pilot attempted a downwind landing. In aviation physics, a downwind landing forces a dangerous trade-off between airspeed and ground speed. The wing needs a certain airflow, airspeed to coefficients to keep flying. With a tailwind, the aircraft's speed across the water rises for the same airspeed, and that extra ground speed translates into extra kinetic energy at touchdown. On that December day, the Heinkel hit the water hard. Drift and uneven surface conditions can push a float plane off-axis at first contact, introducing side loads into a structure built primarily for vertical impact loads. The Heinkel 115's float and strut geometry was engineered to absorb compression from landing, not sustained lateral shear. The port float struts failed under the side load. The wing dipped, dug into the water, and the aircraft somersaulted, capsizing onto its back. The structural integrity of the fuselage held, but the aircraft was now floating upside down. The crew escaped, but the airframe was doomed. Before it sank completely, German recovery teams managed to salvage one engine and both pontoon floats. This explains the asymmetrical configuration found by the sonar in 2005. The wreck consists of the fuselage, the wings, the tail, and only a single remaining engine, all resting inverted in the silt. When the aircraft finally slipped beneath the surface, it did not crash into the bottom, it settled. The heavy engines and wing spar dragged it down, and the soft mud rose up to meet it. Over the next 7 decades, the silt continued to accumulate, burying the leading edges of the wings and sealing the cockpit. This burial protected the aircraft from physical damage like trawling nets or anchors. This creates a complex recovery profile. The team is not dealing with a pile of scrap metal. They are dealing with an intact, upside-down airframe whose seams, lap joints, and enclosed cavities have been sealed by silt and stagnant water for decades. The primary constraint for the recovery is not just lifting the weight, it is lifting it without tearing open those delicate joints, and then immediately controlling oxygen exposure and drying once it surfaces. If the mud is stripped away and the metal is allowed to dry before desalination begins, chloride contamination trapped in the structure can drive rapid pitting and layered damage, including exfoliation in vulnerable areas. But before the engineers could worry about microscopic corrosion, they had to answer a blunt, binary question. Was the wreck inert, or was it still armed? The Heinkel 115 was lost on an active wartime patrol, and that context carried a high probability of live ordnance. And the risk wasn't abstract. The shock and vibration of breaking the airframe free from the seabed could wake 70-year-old fuses. In 2005, following the initial discovery, the Royal Norwegian Navy sent specialist divers to assess the site for munitions risk. Inside the inverted fuselage, they confirmed the threat was real. In the bomb bay, they identified 2 German SC-250 general-purpose bombs. The SC-250 was a standard Luftwaffe weapon, weighing roughly 550 pounds. Reports from the time indicate the bombs were removed from the wreck and disposed of safely under naval control. With that hazard eliminated, the site could be treated as a historic wreck rather than an active danger. This clearance allowed a close-range visual inspection to confirm the airframe's identity and integrity. The divers found the aircraft resting on its back. Salvage history was written into what was missing. One engine gone, float attachment points left bare, and the serial number plate confirmed Werknummer 2398. The inspection also revealed the structural reality of the lift. The aircraft was not just a collection of parts, it was a largely intact airframe. The fuselage was connected to the wings, and the tail section was secure. However, the orientation presented a difficult geometry for rigging because the plane was inverted. The strong points designed to take the weight of the aircraft, the float attachments, were facing upward, accessible to the divers. This was a stroke of engineering luck. It meant the team could attach lifting bridles directly to the factory hardpoints without wrapping straps around the fragile aluminum skin. But the survey also highlighted a critical problem at the interface between the wing and the seabed. The leading edges of the wings were buried deep in the silt. The contact patch was extensive. This wasn't just friction, it was a hydrostatic seal. The mud had formed a vacuum-like bond with the wing surface. If the crane simply pulled up on the fuselage hardpoints, the resistance of the wings in the mud would create a massive opposing force. The wing roosts, designed to hold the weight of the fuel and engines in flight, were not designed to fight the suction of the ocean floor while being pulled from the center. A brute force lift would likely snap the wings off at the root, leaving them embedded in the silt while the fuselage came up alone. The team had cleared the explosives, but they now faced a physics trap. They needed a way to break the vacuum seal before they applied the lifting tension. On June 1, 2012, the recovery team brought a work barge over the site and began the hardest step, breaking the aircraft free of the bottom. The following day, June 2nd, the lift and transfer to shore would be completed with heavier lifting gear. The challenge facing the engineers was a phenomenon known in marine salvage as stiction, or static friction. While the aircraft itself weighed only a few tons, the force required to pull it directly out of the mud was exponentially higher. Stiction happens when a broad surface, a wing, beds into soft sediment and seals out the water beneath it. When the crane pulls, pressure drops under the wing, and the water column above effectively clamps the structure to the bottom. For lightweight aluminum alloy, that differential is brutal. A brute force pull would almost certainly shear the wings at the roots, leaving the team with broken sections instead of a coherent aircraft. The solution was a technique called mud lancing. Before the crane applied significant tension, divers descended with long, perforated pipes connected to high-pressure water pumps on the surface. They carefully inserted these lances into the sediment beneath the leading edges of the wings and the tail section. By injecting water and air under pressure directly into the contact zone, the divers achieved two things. First, they liquefied the packed silt, reducing the friction coefficient. Second, and more importantly, they introduced water underneath the wing structure. This equalized the pressure, breaking the vacuum seal. The water lancing method converted the problem from a vacuum extraction back to a simple weightlifting operation. With the suction broken, the rigging team utilized the aircraft's original design features. The lifting strops were attached to the 4 reinforced hardpoints on the fuselage and wings where the floats had originally been mounted. These points were engineered to carry the entire weight of the aircraft, making them the safest possible anchor points. The crane operator began the lift slowly, monitoring the load cell. The dry weight of the stripped airframe was expected to be around 5 tons, but trapped silt and water inside the structure could push the lifting load significantly higher, at times closer to 9 tons. As the cables tightened, the fuselage broke free from the seabed without structural failure. The airframe rose through the water column in a controlled ascent. At a depth of 65 feet, the operation paused. The team held the aircraft at this intermediate depth to inspect the rigging, secure any loose components, and document what they could before the final rise. At this stage, any trapped air in cavities and enclosed spaces could equalize gradually as the load stabilized. Once the divers confirmed the stability of the load, the lift continued. As the Heinkel broke the surface of Hafrsfjord, the dark camouflage paint appeared remarkably intact. The distinct unit codes, 8L plus FH, were clearly legible on the fuselage sides, confirming the identity of the aircraft beyond any doubt. The water streamed out of the open compartments, and the heavy silt washed away, revealing the metal skin that had been hidden since 1942. The crane swung the dripping airframe onto the waiting barge, where it was lowered onto a custom-built cradle. The physical extraction was a success. The rigorous application of fluid dynamics and patience had defeated the stiction trap. But as the June air hit the wet aluminum, the preservation clock started. The anoxic silt that had protected the plane was gone. Now, oxygen and chlorides were mixing in the rivet seams. The team had to move the aircraft immediately to its new environment before the atmosphere began to destroy what the ocean had saved. The successful lift of the Heinkel 115 created an immediate chemical crisis. While the aircraft was suspended on the crane hook, it was safe, but the moment it was secured on the barge, the exposure to the atmosphere began to accelerate the risk of chloride crystallization. The aluminum alloy, saturated with salt water for 7 decades, was now interacting with oxygen. If allowed to dry, the salts trapped within the metal structure would expand and shatter the rivets and skin from the inside out. The Sula Aviation Museum had anticipated this specific failure mode. Years before the lift was authorized, the project leadership understood that recovery without a stabilization plan was merely delayed destruction. Their solution was to construct a specialized facility on the museum grounds, located just a short distance from the recovery site. This facility, known colloquially as the aquarium, was a large freshwater basin measuring 33 feet wide by 49 feet long, or roughly 10 by 15 meters. The logistical sequence on the ramp was driven by this requirement for submersion. The aircraft was towed to the shore and lifted onto the concrete apron. There was no time for a victory lap. The team immediately began a controlled disassembly of the airframe. To fit inside the treatment tank, the aircraft had to be separated into its primary structural components. The wings were unbolted from the fuselage, the tail section was detached, and the remaining engine cowling was removed. As each section was separated, it was subjected to a high-volume freshwater rinse to remove the surface mud and loose debris. This was a superficial clean. The real threat was deep inside the lapped joints and double skins of the airframe. The components were then lowered by crane into the water-filled basin. The tank was equipped with a system of pumps to circulate the water and sensors to monitor the salinity levels. The process occurring inside the tank is not a quick rinse. It is desalination, a controlled leaching of salts over time. In this context, it relies on a diffusion, because the concentration of salt is higher inside crevices, lap joints, and double skins than in the surrounding freshwater. Chloride ions migrate out of the structure and into the tank water. Over time, the water grows brackish as it absorbs the leached salts. To keep that gradient working, the water must be renewed again and again. As the tank water takes up salt, it is drained and refilled with clean freshwater, sometimes with circulation added to keep the chemistry moving. This resets the concentration difference and pulls more chlorides out of the metal. This is not a quick wash. It is a slow, rhythmic cycle of draining and refilling that must continue until the chloride burden in the structure falls to a stable, low level. The aquarium was designed not just for chemistry, but for documentation. The tank walls were fitted with large glass viewing ports and internal lighting. This allowed the conservation team to monitor the condition of the submerged parts without removing them from the protective fluid. It also allowed the public to view the aircraft in its stabilization environment. While the airframe sat in its freshwater bath, the team began the arduous task of cataloging the smaller artifacts. Over 3,200 photographs were taken to document the condition of every gauge, lever, and panel. This evidence collection was critical. The physical aircraft was now safe from the atmosphere, but it would remain underwater for years. The recovery operation was formally concluded when the last major section was submerged. The engineers had successfully moved the Heinkel from an uncontrolled saltwater grave to a controlled freshwater laboratory. The battle to get it out of the fjord was over. The long process of ensuring it survived the next century had just begun. The Heinkel 115 now rests in the dim light of the preservation tank at the Sula Aviation Museum. It is no longer a wreck, but it is not yet a display piece. It is a patient in critical condition, undergoing a treatment regime that measures progress in years, not days. The aircraft is currently defined by what we can see through the water and what is happening microscopically inside the metal. The visible evidence is striking. Through the water, the white codes, 8L plus FH, still bite through the dim light, a wartime signature that shouldn't have survived. That paint is more than aesthetics. It lets historians verify camouflage patterns and stencils from the Luftwaffe's Norwegian theater, details usually erased by current and sand. However, the real battle for the aircraft's survival is invisible. It is fought against the mechanism of chloride crystallization. This is the specific physical threat that dictated the construction of the tank. During its 7 decades on the fjord floor, the aluminum alloy absorbed saltwater into its porous structure. The metal grains are saturated with chloride ions. If the aircraft were removed from the water and allowed to dry in the open air, the water would evaporate, but the salt would remain. As the salt comes out of solution, it forms a solid crystal lattice. This crystallization process involves a significant expansion in volume. The growing crystals exert immense internal pressure on the metal structure. They push the layers of the aluminum apart, causing the material to delaminate and flake off in sheets. This phenomenon, known as exfoliation corrosion, can reduce a solid wing spar to dust. The force of the expanding crystal is stronger than the binding energy of the corroded metal grains. To prevent this, the tank water is kept fresh and circulated. The process relies on the slow diffusion of salts out of the metal and into the surrounding water. It is a game of concentration gradients. When the water in the tank becomes too salty, it is drained and replaced, resetting the gradient and pulling more chlorides out of the airframe. This cycle must be repeated until the salt content in the aluminum matches the negligible levels of the fresh water. This is not a process that can be rushed. The diffusion path from the center of a rivet joint to the surface is long and tortuous. While the chemistry does its work, the museum team has secured the data. A dense photographic archive captured the cockpit, radio gear, and structural ribs before years in the tank could obscure access. Even if physical conservation faces setbacks, the technical information is preserved. The legacy of the Hafrsfjord recovery is singular. While other fragments of Heinkel 115s exist, usually battered wreckage from shallow waters or crash sites, Varknummer 2398 is regarded as one of the most complete recoveries of the type and a rare reference point for what a Heinkel 115 truly looked like in service. The project is classified as a success not because the plane flies again, it never will, but because the recovery team recognized the limits of their intervention. They did not attempt to restore the aircraft to a false operational status. They accepted the constraints of physics and chemistry. By keeping the aircraft wet, they honored the 70 years it spent in the silt. The success of the operation was the discipline to trade the glory of a quick display for the patience of a long submersion. The Heinkel remains in its tank, a suspended moment of history, held in stasis by the same element that once claimed it.